Instead of just reading data, modern intelligent neural interfaces now maintain a continuous, real-time, bidirectional conversation with living biological tissue. When Hans Berger developed the electroencephalogram in 1924, his goal was strictly observational. The EEG functioned as a passive window into the brain's electrical rhythms. Modern clinical work replaced that passive window with high-density sensor arrays integrated with deep learning models. Current modeling bypasses explicit motor intent to predict latent, unspoken cognitive states. Intelligent neuroprostheses read this raw data and respond by actively steering the user's biological cognitive processing in real time. To evaluate the impact on human autonomy and global regulation, we have to map the exact mechanics of the agency loop. Engineering a functional, high-speed interface creates a systemic friction. The same sensors required for control transform the user's mind into an algorithmic optimization target. Electroencephalography records high-dimensional electrical signals with poor spatial resolution, heavily masked by physiological noise from muscle contractions. Linear equations are mathematically insufficient for mapping the chaotic, nonlinear dynamics of a living neural network. This schematic maps the BCI architecture. Chaotic raw EEG wavelengths flow into the structured layers of a convolutional neural network, which automatically extracts complex spatiotemporal features. By analyzing the sequential relationships between successive neural states, the network identifies historical patterns without engineers needing to define them. For a patient operating a motor prosthetic, these patterns must be recognized in milliseconds. Any latency creates an immediate physical safety risk. To meet that timing constraint, developers compress these models so they can run on embedded processors in real time. This requirement for speed generates an algorithmic black box. The system functions, but developers cannot trace the logic the AI uses to interpret the brain. Within that processing pipeline, the neural network separates the raw data into distinct frequency bands. This extraction enables affective computing, the automated recognition of human emotions through biological markers. This data visualization shows the isolation of frontal alpha asymmetry and theta activity from the background noise. In a clinical setting, extracting these exact signatures allows an algorithm to predict a patient's treatment response to depression with 84% accuracy. The signal processing required to move a digital cursor automatically captures these psychiatric markers. Machine learning models use these unique neural patterns to execute brain fingerprinting, identifying individuals and their hidden psychiatric traits. This follows Benjamin Libet's readiness potential principle. Predictive electrical signatures fire in the motor cortex hundreds of milliseconds before a person forms a conscious thought. Consumer wellness applications harvest this neural data under broad terms of service, exploiting the temporal gap between biological intent and conscious awareness. Traditional informed consent fails in this context. A user cannot meaningfully consent to the extraction of psychiatric states they have not yet realized they possess. The training datasets for these models are sourced almost exclusively from homogeneous Western populations. Neural data is heavily influenced by physical and cultural variables, making the concept of neurological objectivity a myth. Variations in skull thickness and hormonal levels drastically alter how an electrical signal attenuates before it reaches the sensor. Culturally, different demographic groups exhibit distinctly different neural activation strategies to solve identical cognitive tasks. This comparative matrix demonstrates the result. When a base model is applied globally, classification accuracy drops and false positive readings spike. Machine learning algorithms optimize for the majority class. The decision boundary shifts to favor the primary dataset, exacerbating these baseline biological differences. This is algorithmic neurocolonialism, the systemic imposition of localized neural norms onto diverse global populations. This introduces a global medical risk, as automated systems misclassify natural biological variants as neurological pathology. To solve extraction errors, engineers deploy closed-loop adaptive systems in deep brain stimulation and motor neuroprostheses. This is the agency loop, a bidirectional optimization process. The machine learning decoder constantly recalculates its mathematical weights based on user feedback. Simultaneously, the human brain unconsciously alters its own firing patterns to make its signals easier for the machine to parse. In stroke rehabilitation, this loop is highly effective for driving neurological recovery. However, applying this continuous feedback loop to psychiatric patients or healthy consumers introduces severe ethical vulnerabilities. Hyper-optimization can lead to oblomovization, a state of profound cognitive lethargy where predictive algorithms anticipate every intent before it is formed. Users develop an existential dependency on the device for basic emotional regulation. The agency loop dissolves the boundary of the self. When a human brain wires its synapses specifically to be parsed by an algorithm, cognitive autonomy is lost. Translating these closed-loop systems from laboratory theory to scalable medical devices is currently fraught with institutional friction. Developers face a mathematical paradox. To eliminate algorithmic bias, they require massive, iterative, real-world data from diverse populations. That requirement collides with the rigid reality of the European Union's medical device regulation. The MDR treats dynamic, continuously learning AI systems with the same static rules used for physical hardware, effectively stalling legal adaptation. In response, international bodies are drafting new frameworks to account for the unique mechanics of neurotechnology. Initiatives from UNESCO and the OECD focus on global neuro-rights that legally protect mental self-determination and cognitive liberty. Legal frameworks cannot solve the underlying engineering problem. Safely deploying closed-loop systems requires explainable AI, where engineers can audit the exact mapping between a brainwave and a machine output. This requires ethics by design, where transparency and privacy safeguards are integrated into the BCI architecture itself. Transparent, auditable engineering is the primary technical safeguard for maintaining the human mind's status as the sole author of its own actions.